welcome back to my lab. As promised, we're going to go over the software that controls the oven. Let's start with the HMI. That thing is built on Universal Windows Platform, which is programmed in Visual Studios. And it uses something called XAML. It stands for Extensible Application Markup Language. Right? It's really just a scripting language that defines how things look. So first, let's look into how we would set up the programming environment. So just grab the Visual Studio's installer from the website here. Then when you run the installer, you can go ahead and select everything that you need to develop. We'll use the Universal Windows Platform development in the top left, and this code is actually built on an older Windows 10 SDK, which should be down in the bottom right. Once you have everything installed, we'll still need to add a NuGet package source, and we're going to be using a library package called Syncfusion. This is where we're going to get some nice things like the graph that we're using. The link to that source will be in the description. Okay, now we can go ahead and get the code from GitHub. This is really convenient in the newer versions of Visual Studios. You can just click on clone over here, then type in the URL here for the code and figure out where you want to put it. And then you can just hit clone. We're getting a weird C++ error here, but we don't need C++, so let's just ignore it. Once we open the solution, it'll automatically bring up a settings area where we can turn on developer mode. We're going to need developer mode if we actually want to use anything we make here. It's a security feature in Windows, and we're too cool for security features. Then let's right-click on the solution and hit Restore NuGet Packages. What this will do is go ahead and download all of the NuGet packages that we're referring to. Then we have to create a certificate because more Windows security features. You can just create a certificate by hitting the Create button there, and then just type in a name and a password. This is for any computer that's not set to developer mode. When you go to install this application on another computer, it will go ahead and ask if you want to trust the certificate. Then it will go ahead and trust everything from the publisher name that you see here. Then from here we should be good to go. First of all, let's do a little recap on the screens that we have on the interface. First of all, we have the main screen, the operator screen, whatever you want to call it, that just does the basic control through the buttons up top and also just displays the graph. Besides that is the recipe setup screen, which we're about to go into, but let's cover the rest first. To the right of that is where you save and load the different recipes, so you can give them names and save them for later. I think that's pretty much self-explanatory. And then besides that is the PID tuning screen. So the recipes are essentially just an array of points, all defined by a temperature and a timestamp. And when we are actually doing the temperature control, a line is interpolated between the points to give us the target temperature at any given time. So if you look at the interface here, we have to be able to add and remove points and then define each point in the process, and then it displays it on the graph there. So let's just go take a look at all the code that makes all of these pages work. If we click on mainpage.xaml, we can see the entire XAML markup here and its resultant screen. You can select the size and scale and its orientation. This allows you to see how it'll look on different devices. Of course, right here we're only using one kind of device, so we don't care. So you can see the markup language here defines everything that you see on the screen and sets up the events that will also trigger all the code that we're using. Now let's go look at the C# associated with this page. If we open up mainpage.xaml, you can see mainpage.xaml.cs. This is where the code that is actually triggered from the main page is defined. A quick side note that'll make your life so much better. If you open up a program in Visual Studio, it opens up all the code sections by default, and that really makes it a nightmare to read. So what I like to do is use Control-M, Control-O to collapse everything. This makes it much easier to look at the program from top down and just see the overall function of the program and then just look into whatever you want. See, now isn't that so much nicer? So let's step through one piece at a time here and talk about it. So main page here is just the constructor for the class, which just means that it's going to run once and it initializes everything that needs to be initialized. Main page loaded is actually going to be called every time the main page is loaded, but in this program it's only going to be once, so this also only runs once at the very beginning of the program. This thing also initializes some stuff. It loads the recipes from the file system, starts the sample timer that just from now on will go around taking the samples periodically and updating the graph. One of the quirky parts of this here is that you'll notice it actually restarts if the oven tells us that we need to restart. This is a little quirk of the hardware that I set up. I routed the 12 volt power to the display panel and the Dragon board, and when the power turns on at the same time, they both boot up at the same time. And because they both boot up at the same time, they don't establish a connection properly. So the way we kind of hacked our way around this is to have the microcontroller actually tell the HMI that it hasn't restarted yet. Then the Dragon board restarts and establishes a proper connection to the display panel. That's really dumb, but it's what we have to do on this one. In the future, I'll just use a Windows 10 tablet. Turns out they're about the same price anyway, so there's no point in building up our own. And this will just enable the recipe send button every time the recipe is changed, which makes sense. The next section here defines the lock screen, which will come up after a certain amount of time of not interacting with the screen. Then you have to swipe along the screen in order to remove the lock screen so you can go back to editing things. It just prevents accidentally changing things in the middle of a test. You can see that there's a timer here that once it stops, it sets the lock screen to visible, and if there's a page input from a pointer or a keyboard, then it sets the lock screen to collapsed and resets the lock timer. One interesting note about the lock screen is that we wanted it to be transparent so you could see through it. But if you make it perfectly transparent, then it's actually transparent to input as well, which completely defeats the purpose. So we've made it trivially non-transparent. And so if you make a lock screen and you're wondering why it doesn't actually stop you from inputting, just try setting a 1 in there for the alpha. The next section here just defines the pop-up dialogs, which I think is pretty self-explanatory. The only thing interesting that we're doing here is we've got a little wrapper that wraps the usual show dialog function, but here we actually add what's called a semaphore, which just means that only one of them can actually access the dialog at a time. So it means if you do end up getting more than one dialog, they'll take turns showing on the screen. That's just a nice convenience, because if you try to open up 2 different dialogs from 2 different events, then it'll throw an exception and crash or something. So this just prevents anything from even trying to open a dialog if there's already a dialog open. The next section here is everything associated with the operations tab, the first tab in the HMI. Here we have a sample poll tick, which is the timer that just runs periodically and gets the sample from the microcontroller. This is the one we initialized earlier. So you can see it calls the update sample UI function, which is just a little bit down. This is what'll update the just the values displayed on the screen. Then it'll add the sample to the graph, which this graph is from that Syncfusion library. And when you add a sample to the graph, it automatically redraws the graph with that sample. So we don't really have to do anything more with that than this. Then also here you see all of the functions for the 4 buttons on the operator screen, or the operations screen. The only thing really interesting in here is that on the stop, we actually take the current data from memory and create a CSV of the entire cycle. The next section handles everything associated with the recipe edit tab, the second tab in the HMI. Here you can see we have the handlers for the add and remove step buttons, and the handlers for when you change the values of the actual steps. Then we have the recipe save tab, which is just a couple of handlers for the save and load buttons and file system management stuff. The final tab is very simple. It really just handles the PID values and sending them and loading them from the PSOC device. That's everything for the main page handling code. So let's move on to the oven. The oven, like I said earlier, is actually the PSOC microcontroller. This section of code handles everything to do with the communication with the microcontroller. And this includes another semaphore so that we're only sending and receiving one message at a time to make sure that we don't screw anything up. All of these functions should be pretty self-explanatory. If you want to get into them, you can look at them on the GitHub. You'll notice there's a lot of bit shifting and all that nasty stuff you get into when you get into communications. If we move on to recipe.cs, we can see the recipe is just defined as an observable collection of the class we're calling temperature time. So each one of these is a step in our recipe. This class definition is quite convenient. The time and temperature here is stored in raw 16-bit integers that the microcontroller is using, but is automatically transferred to and from the time and temperature that the HMI likes to see. So if we update the time in the HMI, it automatically converts to raw time and stores it in the unsigned 16-bit integer. And if we look at the sample class definition, it's defined in a similar way. We get the raw values from the PSOC and it conveniently transfers that over to something that's a little bit more friendly for our HMI. The helper class here is some extensions to the Syncfusion controls because they're not strongly typed, which if you don't know what that means, that's not too big a deal, but it ends up resulting in us getting values back that are not something we can rely on. Sometimes they're floats or integers or even sometimes strings. So these extensions here are kind of a hack to get around that, to convert from everything that we might possibly get from those functions to something, the thing that we want. So just know that they're not actually a part of the library. We added these for our convenience. So that is a top-level overview of everything in the HMI, which I know this is a lot of code to just kind of go over without having any confusion at all. So if you have any questions, feel free to leave that in the comments, and I'll try to be as clear and concise there as I can be. But that concludes the HMI code. So now let's move on to the microcontroller, and this is going to be the Cypress PSOC that we like to use. The HMI is going to be talking to this thing through a serial USB connection. It's just a nice, easy connection to set up. So the HMI just controls the system by sending the basic commands and the recipe set points, the array of recipe set points, to the microcontroller. Then beyond that, everything else in the control scheme is done by the PSOC microcontroller itself. I like to do this because I like to design systems where even if you unplug the HMI, the cycle should still run. You shouldn't actually require immediate intervention from the HMI during any part of the process. That way you can still have it observing the process, but I don't like to make it so that you have to have that thing intervening at any point or relying on that connection. That just makes machines that are more robust in general. So the PSOC microcontroller just takes all of the set points that it was given from the HMI and does the interpolation itself. So the actual target temperature from the recipe at any given time is actually generated inside the PSOC itself. So that and all of the data that is collected by the microcontroller is used to run the entire control loop. So let's go take a look at the microcontroller code. Let's start with the hardware configuration here. We have a USB block here, and if you just drag out a USB UART block, that will make a USB pre-configured for using as a serial port. If you want to know more about how to set up one of those, then you can look at our previous tutorial on the subject. Now here's the PWM that is going to be controlling the heater element, the power going to the heater element. We have a period of 119 here because that will allow us to have 120 steps if you include off being one step. This is a convenient number because there's actually 120 zero crossings in the 60 Hz sine wave, and our solid state relay actually turns on and off at the zero crossings. Here you can see the pin configuration for the element PWM and also the element enable. Element enable actually controls the redundant relay that is in front of the solid state relay. Like I said in previous episodes, solid state relays, when they fail, they tend to fail connected, so we want to mitigate that risk by putting a regular relay in front. And here we have a hardware timer that we use to count the number of seconds that have passed since the beginning of the recipe. Then we have a pin here for the one-wire communication that goes to the thermocouple. Here you can see the pin definitions that we're using on our particular project here. And from there we can move on to the code. Here we have the handling for the Hmi Communications, and mostly all I can say here is that this is also the usual bit shifting that you get when you're dealing with communications. Then the other communications that we're doing here are going to the thermocouple. And here we're just having the CPU manually turn pins on and off to work out this one-wire communication protocol. And that's typically referred to as bit banging. If we wanted this thing to have some good speed, we would actually probably define a universal digital block to do the communications for us, but here we have tons of CPU and not a whole lot to use it on, so we'll just go ahead and have the CPU handle the communications here. Now for the main code. You can see the beginning initializes everything we need, as you would expect, and then at the beginning of our for loop, you see we update the thermocouple reading, and we update a couple of other things and the communications to the HMI. Then you see the if status is running. That handles all of the logic when the oven is actually running. At the beginning of that, you see the startup code here, which will just run once at the very beginning, which initializes the beginning state of the cycle. So you can see we energize the enable element relay and reset the recipe timer. It also clears out something we're calling laggy power, but we'll get into that in a second. The next if statement here triggers periodically to run the control loop. The front end here is looking at the next step in the recipe to figure out how much energy we're going to have to put in to get to the next step by the time the next step comes around. Then we have this prediction recipe step is greater than 0, which just ensures that we're on a valid recipe step. And then we get into the meat of the control loop. And it's about as mathy as you would expect. So let's take a look here. This is all the normal control loop stuff here. We have a PID like we mentioned in previous videos. The important thing to note here is that we are using the temperature model that we derived earlier to linearize the PID. One thing that's in here that we haven't actually talked about yet is this laggy energy thing here. We have this here to account for the fact that we're actually heating the refractory stone at the bottom of the oven, and then that refractory is heating up the rest of the oven. So we are expecting to see that energy in the temperature of the oven later on, but it takes a little while for that heat to propagate from the coil to the stone and then to the air in the oven. So the way that we're implementing this here is that we have a sort of rolling buffer that integrates all of the energy that we've put in for an amount of time in the past. The time that we look into the past is actually a tuned constant of the oven, which right now is about 140 cycles of the control loop. Then after we've added the previous energy that we put into the laggy energy, we go ahead and calculate the desired output power using our previous thermal model. We add the thermal model to the PID power that we calculated before to create the final output power to the element. Then you can see we set all the PWM values, and that's the end of the control loop. Then at the end of the file you can see the else statement that handles the case where we are not running, which just makes sure that everything is stopped. So that's everything that the microcontroller is doing. Other than the dense bit of math there, it's pretty easy to get through. So as I said earlier, if you have any questions, go ahead and leave those in the comments and I'll do the best I can to answer them. I have actually gone ahead and done a little powder coat test already, and it turned out quite nicely, so I'm going to leave you with some video of that. So with all of that said, thank you for watching. We'll see you next time.